Good morning. Welcome to Krishna's class. Sorry, I was a bit in this, and that is why I did not turn up for some time. Now, let us start with a new topic. In fact, you recall that we have explored LP spaces in general, and we have found that they constitute a a complete normed linear spaces. So each LP is a complete normed linear space. So we are taking X as the measure space, and the LP functions are defined on that a complex value. Okay, now what we have is the following. Complete normed linear spaces are called Banach spaces. So we know the structure of LP spaces. It's a normed linear space. It's a complete normed linear space. Therefore, it's a Banach space. A nice ground on which you can play analysis. Now we are planning to look at the special case L2, that is P equal to. Why this? Now this is the first question. Having explored LP completely, why do we want to come back to L2? There is a reason, because it has some very special structures called the inner product structures. And that makes it very fascinating. And before we go to look at LP, L2 mu, look at the classic two or three dimensional vectors. You can look at their structures. So what we are interested in, the so-called R2. So you might ask why I omit R1. R1 is omitted because it is non-visible. See, R1 is omitted. It is too simple. But R2 and R3 are the space of vectors. So R2 is a two-dimensional vector. And R3 is Why these two? Because you have a visual perception of these spaces as vectors in a plane and vectors in a space. So these are vectors in a plane and these are vectors in a space, where you can conceive things and have a feeling for them, or in fact you can touch them. Okay. Now let me just formally write what it is. R2 is with respect to a certain basis is the ordered pair x1 x2 so also R3 is and the whole concept comes out from physics, not from mathematics. Do involve vectors, scalars and vectors like velocity, acceleration, then force, and so on. And this collection of objects, the mathematicians naturally looked at these as individual entities, but as collection of entities of the same class. And of course, from the theory of linear spaces, you know that they have representations like this with certain basis chosen for the space, and R2 is a three-dimensional vector space. So you have a basis for R2 consisting of two linearly independent vectors, and R3 has a basis consisting of three linearly independent vectors, although they are not unique. So you have representations of this kind. So having fixed the basis and representation, this will be working. Now you see, abstractly, one can, if U is a vector, I am talking about vectors in R2 or R3 in a plane or in space, and V is a vector in V, then parallelogram law gives a mode of addition of these vectors. For simple, this is the structure of R3. Is a vector, E is another vector, then they add up. These vectors add up using the parallelogram law. That means U plus V is a diagonal of the parallelogram with U and V as sides, and this is U plus V. This is the addition that you do. Likewise, I am working in R3. So, see, these are the, I have put a coordinate system just to convince you that I am working with vectors in R. This is U plus. And this addition, as I have done in one of my earlier lectures, that is not what mathematicians invented, but forced by nature and discovered by physicists. Okay. What is the rule of addition for forces? What is the rule of addition for velocities? What is the rule of addition for acceleration? Then experimental results suggest that they add using the so-called parallelogram. It has nothing to do with mathematics. So you have the vector addition. So also you can scale the vectors. Again, if you have a vector u, then you have lambda u positive. The reverse direction, this is mu negative. So you can scalar multiply, or you can change the magnitude of the vectors and not the direction by multiplying by a positive scalar and multiply by a negative scalar or real number to reverse the direction, and you get mu. Then the vector mu will be in the opposite direction, and so this is how the new vectors can be generated from, and new vectors can be generated from two given vectors by using parallelogram. Okay, so this is the situation that you have. So you have the concept of what are called sum of vectors and scalar multiple of sum of two vectors is again a vector. Scalar multiple of a vector is again a vector. And you have the zero vector, which is obtained by multiplying any vector or annihilating by multiplying it by 0. So there is a zero vector. There exists a zero vector. So you now, as it is the case, usually by mathematicians, they are not interested in the individual vectors, but they are interested in what are called the whole collection of vectors in R3, whole collection of vectors in R2. R2, whole collection of vectors in R2 are they are called the plane vectors. The other one is vectors in space. So we have a credible way of adding these vectors and scaling these vectors by multiplying by a scalar. Okay. Now with these two operations, okay, one more thing. Once we choose a set of linearly independent vectors spanning space. This is what you call basis. The plane vectors would form, or R2 will be a manifestation of these plane vectors. Okay. So also R3 will be a manifestation of the vectors in space. We have two-dimensional V represented by a copy of R, and three-dimensional copy. Now this A is important here. The particular copy depends on the choice of the basis. These are typical examples of what are called finite dimensional vector spaces. Okay. Then of course you have U can be written as okay. Of course, these numbers are uniquely determined once the basis is chosen. And this corresponds to, so with respect to the ordered basis x1, x2. This ordered basis, so that this representation is unique. Similarly, if basis for R3. Then V E1 is an ordered basis. Now, what is significant is that these representations are not unique. They depend on the basis. Okay. So, that is a remark. These representations are unique and subject the choice of the. So, corresponding to each once the choice of get unique representation R. Now you can see that U plus V this is plane vectors. These are for for three-dimensional vectors. Okay. This is the rule of addition. Scalar multiplication is Now one can connect this with the parallelogram law. So these are coming from parallelogram law. This you can prove it. So component wise addition, now it is very simple. Because once you choose a basis and then the representation in terms of components, the addition is simply adding the corresponding component. I mean, they are real numbers. You have the addition and multiplication there. Similarly, scalar multiplication is multiplying every component by the scalar. Therefore, now we observe that R2 and R3 are abstractly the two-dimensional vector space B, that is the plane vectors, form a vector space, and in space three-dimensional vectors also form a vector space. Using this addition and scalar multiplication. Okay, they are well defined. There is no ambiguity, although the choice of the basis is not unique and the choice of the representation is therefore not unique. Nevertheless, they are all absolutely consistent. Okay, so once you fix your basis, everything is, the representation is uniquely determined. Okay, now you can change. The advantage that you have is that one can choose, given a vector space, one can choose a suitable basis, a suitable ordered basis to get the representation. So that once you do that, whatever is happening in the representative space of R2 or R3, you have the corresponding actions taking place in the vector space. So you have the abstract vector space and the manifestations of these vector space in terms of R2 and R3. I'm not going into R and R2. That is something that you can easily migrate to. Okay. So they are vector spaces. What do we mean by that? The zero vector is this is the zero vector. Okay. And U is into is the additive inverse. With respect to addition, with respect to addition. Begin. That is one structure. So V is a group with respect to addition. Now with scalar multiplication, we have to say how things interact. Now one can see that lambda of then so these are the things that you can do. This actually says how the scalar multiplication interacts with the addition structure of the space, or how the vector multiplication interacts with the addition structure of the field, that is R that we are seeing. So that's the meaning of it. Okay. Then you can see that U, then you have 0 into 0 is a scalar. This is the 0 vector. Okay. So these are the properties that you get. You see that lambda mu so it is defined. Okay. So all these are nice properties. Okay. So this forms a vector space. Thus, if it is two-dimensional, then R2 is a manifestation of so also three-dimensional, then R3 now you see that a few important things that we have to say is that we are talking about two-dimensional and three-dimensional vector spaces over R. And you can have the you can have the represent them by R2 and R3. That is, if it is three-dimensional, then R3 is the representation. If it's two-dimensional, then it's R2 is the representation. Now, there are various representations possible. For each choice of a basis, you have a representation. Okay, right. So, from the abstract space to the concrete space that we are. Now, what more you have on this? Now, you see, in R2 and R3, we can talk about the length of the vector. If is given by this is simple Pythagoras theorem. Similarly, y equal to if y equal to then by the same Pythagoras theorem, this is what you call the length of the vector. Once again, you observe that this is equal to 0. This is the zero vector. Right? This is the triangular inequality. Oh, this is simple. Vectors x and y, then x plus y is this is x plus y. So the norm of or the length of x plus y is this. That is, and you see that the length of this is equal to the length of y. Okay. Therefore, length of x plus length of y is greater than or equal to length of x plus. This is the general property of the length function. So it's a length function. Okay. It is called a norm. This is called or this is what you call Euclidean norm. The usual standard norm. Okay. So that is something additional that you have on this. And you see that in fact, this endows the space with a distance. In fact, this endows metric defined by you can easily show that this is all the properties of a metric. So he defines a metric. So it's a metric space. Therefore, R2 and R3 are situation. Now these are all what is called the Euclidean metric. With the concept of distance between 2 points in space is the direct distance that you have 2 points. The distance is actually this length. Okay. So this is vector. This is the vector. X minus y is actually this vector. This is the vector x minus. So you see that the length of this so this is x minus. Length of x minus y is y. As the distance between 2 points x and y, and you can show that it has all the properties of a metric, namely that so this is the distance function. And that, of course, then R2 and R3 are topological spaces. Metric spaces. That's about the length of the vector. From the length of the vector, you can define what is called a metric, or the distance between two vectors. And this distance between two vectors is essentially the Euclidean distance that you have in this case, and it becomes a metric space or a topological space. Therefore, it's a perfectly nice ground on which you can do analysis. Okay. Now it has more fascinating structures. Probably when we work with LP spaces, you had all these ideas, metric defined, so on. But then it was not a Euclidean space. The structure was quite different. Okay. For each P, the structure is different. So let us explore that for a while. Okay. It's nice to get some insight into the what are called the unit circle or unit disk in the L2 to L or into R2. What is the general norm? See, you have a P norm. This can be one by or even and so this is what you have. So the Euclidean is the special case. Now you recall, associated with P, there is another number called Q, okay, which is called the component, which you call the conjugate exponent. Q is called it's what? You have what you call for P equal to 1, Q is taken as infinity. So that takes care of P equal to 1, Q equal to infinity. These are what are called conjugate exponents. Now let us look at the structure of it. So 2, so this is a very important structure. This is the only case where both P and Q take the same value. Okay. Now let us look at what is the shape of the unit bond. So let us explore this. Very worthwhile to explore this and keep certain things in our mind. That this two, what I want to say is that this two has a very, very special. Now, what is the unit bond? Unit disk P. That's the unit disk. Okay. And D2, of course, D2 is so let us mark these. Okay. Now, this is what you call what? Now we will compare norm x p. So our and the inside and outside. So you see that you can easily see that this corresponds to 1. And And this is the case where you get one. And for all other values, see, goes from 1 to goes from, this is the value 1, this is the value infinity, and this is 2. Now you observe that it's only in the case p equal to 2 that the disk is the interior of a circle in our conventional sense. Okay. In all other cases, the shape of the disk is something different. Okay. So you have got various shapes that you can think of, and you see that this is slightly bulging shape. It's kind. This is for some p that lies between 1 and 2. And here it is going to be again you have so some p that lies between 2 and infinity. You have the ball. So these are all the shapes of the unit ball. Yes. So it is slowly going from a rectangle to another rectangle. But in between, at when p equal to 2, it takes the shape of a circle. That we are familiar notion. Therefore, the geometry of the space changes with the choice of the metric or the norm. This is what I wanted to emphasize. And we are now, because we have seen this specific case. So if you take p lies between 1 and 2, then q lies between 2 and infinity. So p and q cannot be the same. Whereas the only case where p equal to q is when p equal to q equal to 2. They are the conjugate exponents. Okay. In that case, you see that you have a merging of this. You get the conventional circular disk that you have. That's the interesting aspect of this. Okay. So the geometry in the space is determined by the choice of p. So you can attribute different geometries in R2 and analogously in R3. Okay. And in R3, when p equal to 2, you get a ball, a conventional ball as the unit ball. Okay. But when p equal to 2, then the shape of the ball is different. Not the circular, not the spherical one that you have, but it's slightly different type. Okay. So that's something about the structure, and it has its own consequences. Okay. So let us leave it there. So there is some interest for the case p equal to 2. Now we look at the a new measurement that you can work on, that is the angle between two. So in R2, now let us define between two vectors x, y, we define something which we shall interpret later as x1, y1 plus two this is in R3. This definition, at the moment, let us not bother about this. Shall just explore a few facts about this to make some computations and make some interpretations. Now you see that, observe that. In R3. This is something so easily. Now, some of the other observations that we make is easy to. This is true for both R2 and R3. So also so some observations of what we have defined here. This is our basic definition. We are just verifying this, and these are very easy to verify. Now you see that now you can get all the out of it. Well, this is very easy to. We shall keep. So you know that for a given pair of vectors x and y, this we call the inner product. What is the geometric meaning? So let us explore that. In R2 or R3, irrespective of whether you are in R2 or R3, you can make the following. x, y. These two vectors are given. These are given. So we will compute the angle between x and y. How do we do that? Project this. So have OA, OB, and then project OA y onto OB or Kollam. This point you note by OC be the projection. We don't know where it is, but we know that is the axis are such that OC equal to R times, this is the important, OC is equal to R times. Okay. So you have a right angle triangle. So OAC let theta denote angle between x and y. Then first thing that you have to decide is this is Rx. So what is R? So there are two things to do. So we know that cos theta is equal to OC, length of OC divided by length of let us compute this. Before that, we have to say what C is. C is not arbitrarily chosen, but C is the point such that, or C is such that and is along this direction and is the base right-hand triangle, right-hand triangle. Oh, yes. Therefore, we shall calculate to know. So what is R? R is uniquely determined. Uniquely determined. How is it? By Pythagoras. Cap OA square. So let us calculate this. So R we can therefore, that is, you have OC is Rx. AC is what? AC is actually, complete this. This vector is actually, see that this is y minus Rx. This vector is y minus Rx. Therefore, this is the equation. So R is determined by this equation. Okay. So we have to work it out. So this is, we have seen that this can be written as let's work it out. So this is R square plus expand this. So you get this as y norm of y square plus minus therefore you get, after cancellation, get twice R square norm of x square or this is what it is. Therefore, either r equal to 0 or so either so we got r. Now we use this to calculate. Therefore, what is it? Therefore, this is r square square. So if x is not equal to 0, then of course x not equal to 0. Now what you get? Length of OC is essentially the square root of that. Xy divided by therefore cos theta is equal to So this is what you get. Okay. So we are looking for an expression for this. So it's essential. Norm of x, the length of x, length of y into or cos theta is a measure of. So theta is measured. Therefore, x1 y1 if unit vectors along x and y then cos theta is the angle between and you see that this is less than or equal to 1. This is the Cauchy-Schwarz law. So we will I write this as part 1. And my next lecture will be part 2 from vectors to L2. Okay, so this is the angle between two vectors. So you have, suppose this is the unit vector x by norm x, and this is the vector then you have the unit vectors. The unit vectors are of length 1. So this is x by, this is y by, and this is the angle between theta. Cos theta is that's the relation has this angle between them, and this is essentially so you know what exactly this. Okay. Or in other words, you have so that gives a measure of the angle between students. Okay, so these are some additional structures that you have, and the inner product comes out of this. Relation. In fact, for ordered pair xy, we are associating a number. That number has to do with the angle between students. I think I will stop here and continue from here and then take you to L2, the more generalizations of this. Okay, so thank you very much. Happy to restart the series of lectures. Thank you.